Hi, I'm Công Nguyễn. I'm a front-end engineer currently located in Ho Chi Minh City in Vietnam. And I work as a member of Creative Lab project. I joined Creative Lab team in 2020 when the team was starting on the implementation of video editor. Today, I would like to talk about Creative Lab service in the view of a front-end engineer, including a few background story about the reason why we built it and how we built it. We would also like to share our vision for the future plans of Creative Lab. So, what is Creative Lab? Creative Lab is the convenient tool for advertisers to create image and video and export them as advertisement creatives online service. The video you have just watched is a small advertisement created by our video editor. Follow me to the end of this presentation to understand how we build that video editor. As live users yourselves, you must be familiar with advertisements randomly shown on your timeline or live news page. Now, let's take a look on how advertisers use to create campaigns to advertise online. Let's face the truth. Not all of us can draw, and not all advertisers know how to create an attractive image or video for their own advertisement. Before Creative Lab, many advertisers found it difficult to create beautiful creatives. A lot of them, especially small and medium business advertisers, had to spend money on hiring designers or agencies to create creatives so that they can import in Live Ads Manager to create campaign. The more money they spend on new advertisement means the more money they have to pay those agencies. It could get expensive really fast, and it could get even more frustrating if users don't convert to sales. A part of the reasons why Creative Lab was born is to solve this problem for advertisers. So now, with a Live Ads account and a few clicks, drags and drops, user can conveniently export not only single but multiple creatives to Live Ads Manager to create campaign with them. How can we do it? I will explain in a few seconds. Creative Lab service allows users to cook creatives of their own taste. With the help of two main editors, image editor and video editor, all you need to have to start is a Live account. Creative Lab starts out with only the image editor, which consists of 4 kinds of layers: image, shape, logo, and text. Users can easily upload their own images, drag them around, add multiple layers of shapes and text, then export into creatives with multiple ratios. In the video editor, along with layer, we introduce 2 more definitions: scene and transitions. The video editor also supports 4 types of layer, but it's a little bit different from image editor. Shape is replaced by a new layer type called sticker. By composing layers together, we can create a scene. And by composing scenes and transitions together, we can create a video advertisement with multiple output ratios. To bring even further help to users who struggle with ideas, Creative Lab provides hundreds of templates designed by top designers from Line. Users can easily filter by target country, language, industry, even color and mood to select the suitable template to start customizing into the own creative. Before going into the technical detail, I will introduce to you how Creative Lab works in simple words. The relationship between users and Creative Lab designers, and what components Creative Lab editors are made from. Not only Creative Lab provides tools to create advertisements, but it also provides ready-to-use advertisement templates. These templates are created by the experienced designers from Line, and users only need to choose the right template that they want, make some change with the editor, and have a brand new advertisement for themselves. By providing design templates, Creative Lab is saving user time and giving them the best experience in creating advertisements. Creative Lab service provides different kinds of editors, and their general architecture is composed of 4 components. A set of tools that allows the users to edit the advertisement template. The preview component, which helps the user to see what the creative will look like before rendering. In case of image editor, users can edit the template by interacting directly with the preview component. The advertisement template itself, which contains all information of the advertisement. And finally, by rendering, we will turn this template into the actual creatives for advertisement. Not only image editor, but also video editor follows this architecture. For the rest of the talk, I will focus on technical detail of how we turn the advertisement template into the actual advertisement. Let's take a look at the image editor, the first editor we build when we start Creative Lab. In the image editor section, I will talk about the high-level architecture to bring you guys to the overview of the image editor, followed by its layers, including image, logo, text, and shape, which bring you to the specific view of the image editor. And finally, I will cover the technical challenges that we encounter while building the image editor. Let's start with the high-level architecture. There are many options for users to use to create creatives for advertisement, and using a template is one of them. As I mentioned earlier, for the convenience of creating advertisement, Creative Lab provides users with a lot of design templates. All they have to do is picking one of them and start editing. Users, after choosing the design template that they want, can use the image editor, which includes the editing tool and the preview component to edit. They save into their own template. With one more step, which is rendering, users can create an image advertisement based on their template. In image editor, we support 4 types of layers: image, logo, text, and shape. Let's start with image and logo. Image and logo are assets of users. That means they have to upload those resources to Creative Lab first before using them. By uploading, users are free to choose their own images and logo to create advertisement. After uploading, users can start adding these layers to their image advertisement. For the convenience of adding text to advertisement, we support many fonts in different languages: English, Japanese, Thai, and traditional Chinese. In order to add text to image template, users can switch to the text layer panel, choose the font of their choice, and start writing. Unlike other layers, shapes are provided by Creative Lab designers. And currently, we support hundreds of different shapes. The only thing that users need to do is choosing the right shape that they want and use it. Fonts loading and shape are two technical challenges that we encounter during the implementation of image editor. In the following section, I'm going to share these technical challenges in detail and solutions for them. Let's move to fonts loading challenge first. In the supported list, there are a lot of fonts that have large size, and loading these fonts over network could affect the user experience. Suppose that for the worst case scenario, there are 15 text layers with different fonts, and they're all large ones. We have to load hundreds of megabytes over a network, and to us, it was a big problem. We did our research and we came up with two solutions, font server and font subsets. We'll talk about the first solution. With font server approach, instead of downloading a whole font file, client-side will send the format information including text input, font, size, style, and others over a network to the font server. This font server will generate an image of text based on the information it received from client-side. After generating, the font server will send that image of text back to the client to render. Splitting the original font into smaller chunks called subsets and only load a few of them on demand is the next solution. This technique is called font subsets, and it requires 3 steps to implement. Splitting a large font into smaller subsets. Using font face rule to register each of these subsets with browser. Using a Unicode range descriptor inside the body of font face for every subset to define a valid Unicode range. After these steps, browser will try to fetch the needed font subsets based on the input value of the user. Considering the worst-case scenario above, with this approach, we only have to load a few hundreds of kilobytes over a network, which will in the end obviously improve user experience. There were pros and cons when it came to these solutions. With font server approach, the time it takes to generate and download an image of text is faster than the time it takes to download the whole font file. However, if users change the text format frequently when they are editing a template, a lot of communications back and forth between browser and the font server are required. As a result, the preview feature will not be smooth, which in a way is also considered as a performance issue. With font subset approach, the benefit was very clear to us. Browser will only have to download the needed subset files for a specific text input instead of downloading a whole font file. However, this approach would require us to split the original file of every font. In the end, we determined that the font server approach did not satisfy what we needed. And so we decided to choose the other solution to deal with large font size problem. So that was how we deal with font issue. Now, let me tell you about the challenge we faced regarding the implementation of shapes. Shapes are provided by creative web designers, and they want to create them without any restrictions. Frontend developers will receive those shapes apply them to the image header. Inside the header, shapes needed to be freely resigned without affecting the quality. That's what we needed to implement, and we came up with a candidate called SVG. SVG is a vector image format. It uses geometry forms such as point, line, curve, polygon, and so on to represent different parts of the image. And each geometry form has a mathematical formula. In the end, SVG only stores mathematical formulas that can be used to construct the image instead of storing information of all pixels. So SVG can be freely resigned without affecting the quality. Additionally, Creative Lab wants to let users apply stroke for every shape if they want. Stroke is basically about the rough shape. However, the size of SVG is constrained by its width and height attributes. Adding stroke, meaning adding more space to the original SVG. And when the size, including the stroke, exceeds the maximum size, the outer part would not be drawn. As a result, we will end up with a completely wrong shape. The solution for the above problem is related to path to the object. Path to the help us to declare a path. A layer can be used by any path APIs of Canvas. That means we can use path APIs in combination with path to the object to draw every shapes on Canvas. Path to the is also available on most modern browsers, so we can safely use it in our application. To solve the above problem, we need an intermediate step, which is converting the original SVG to path to the object. After converting, we can use path APIs of Canvas to draw the perfect strokes without having to worry about the original slab shapes. By looking at the example, you can also see that some parts of the stroke already have surpassed the original slab shapes. However, they're still properly drawn thanks to path to the. Following the image editor, I would like to introduce Creative Lab Video Editor, which was released earlier this year. What I am going to cover will not be very different from the image editor. However, there's one more part, which is video rendering. Let's take a look at them one by one. The high-level architecture will be shared first to help you guys have an overview of the video editor. After that, I will talk about 4 layers: image, logo, text, and sticker. In the video rendering part, I will introduce the methods that we have tried to create videos on both client side and server side. And finally, I will cover the technical challenges that we encountered while building the video editor. Again, let's start with the high-level architecture. Creative Lab Video Editor architecture consists of 2 parts: a front-end application that allows the users to create or update video templates, and an encoding server that produces MP4 videos by receiving the video templates. Similar to the image editor, Creative Lab designers also create a lot of video templates, and users can choose any of them and start creating their own video advertisements. Users can use the editor to update the video template, save to the old template collection, and finally, create video advertisement by rendering. Under the hood, we do this by sending the video templates to an encoding server to produce an MP4 video. As I mentioned earlier, Creative Lab supports 4 types of layers in the video editor: image, logo, text, and sticker. Image and logo are the assets of users, and they are shared resources between image and video editors. So Users only need to upload these types of resources once, and they can use them in both headers. Once uploaded to user asset, these images and logos can be added into the video advertisement through the setting sections. Text layer in the video header is almost the same with text layer in the image header. All fonts supported by the image header are also supported in the video headers. In order to add text into video template, users open the text setting, start writing, and then select the correct format for the text. Just like the shape layer of image header, hundreds of stickers are also provided by creative web designers under many categories. Users only have to pick the right one for their video advertisement. Technical-wise, since stickers can contain text in various fonts, we simply treat them as PNG images instead of SVG. In general, a video is created with two steps, drawing and encoding. As you probably know, drawing is the process of grading video frames, and encoding is the process of merging these video frames together in an efficient way to optimize the output side. As for drawing, we use canvas element as a container to draw graphics on. To be specific, what we use from canvas to draw were both 2D and WebGL context. As for encoding, in order to finalize the method that we use for creative web, we consider media recorder API, FM pack, and hardware encoder. Let me share with you what we have tried and how we came to the conclusion of our final technical stack. First, let's see how we try to apply drawing for videos. In order to enable GPU hardware acceleration, we decided to use WebGL. For those who haven't heard of GPU hardware acceleration, it's a way of utilizing the parallel computing nature of GPU to make practical computation faster. WebGL provides APIs that allow us to communicate with GPU in a reliable and efficient way. What we love about GPU is that graphical computation that runs inside it is really fast, but it doesn't mean it's always fast in every single situation we use GPU. For instance, when the application has to upload a large amount of data from CPU to GPU memory to draw, or when the application requires a lot of communication back and forth between CPU and GPU, it's possible that we end up with a performance issue. In our case, as for now, the animation created with WebGL are using the same resources. Therefore, it doesn't create such a big impact on performance. Why using WebGL? There are two properties that we have to notice. Always upload all resources to GPU memory before drawing. And all resources must be images. Among layers, text itself is not an image. We therefore had to find a way to convert text layer to image before the uploading process happens. The method that we chose was drawing text to canvas with the correct format and then get back the image as resource. Text chains are expensive since we have to convert text values to images and upload them to GPU memory again and again. In our implementation, we try various techniques, including cache, to reduce text chains and save performance. So that was about drawing. Now let's talk about encoding. Among the methods for front-end developers to create videos on browser, we consider Media Recorder API. Media Recorder is a browser API that creates a video by recording a media stream. Within browser, There are various ways to create media stream, and one of them is using Canvas element and its capture stream API. These days, Media Recorder API is available on most modern browsers. That was the first method that we tried in order to create videos on client side. Apparently, this method has quite some disadvantages that affect the user, which led us not to use it for a real service. We will talk about them more in the technical challenges section. At some point, after a few trials, we start to realize that to serve the amount of requests needed for Creative Lab, creating videos on client side was impossible. And we start looking into the server-side rendering option. FFmpeg is a well-known method to create video on server-side, and it's also available as an npm package, so we can use it within the Node.js environment. FFmpeg basically takes video frames and some other encode options as input and returns video as output. Media Recorder API and FFmpeg are accessible methods to create videos. However, we also found a very efficient way to create videos, that is, using hardware encoder. On server side, we added GPUs to speed up the process of creating videos. In each GPU, there is a hardware encoder that we can use to encode videos. In order to communicate with the hardware encoder, there is a low-level SDK that acts as an interface between us and the hardware encoder. Unfortunately, the low-level SDK was written in C++, and our encoding server used Node.js as a runtime environment. This means we cannot use the low-level SDK directly in our code base, and we have to create a Node.js binding library for that SDK. Node.js binding opposes APIs that can be used directly in Node.js. These APIs, in reality, just running C++ code behind the scenes. While implementing the video editor, we encounter many technical challenges such as encoding speed, difference of text between client and server rendering, and support new effects. In the following section, I will share these technical challenges in detail, the solution for them. Let's take a look at the encoding speed, a technical challenge that we encounter at the early phase of video editor development process. Media Recorder API has advantages and disadvantages. It's very easy to implement. However, what Media Recorder API actually does is to record a media stream to create a video. That means the render time will be greater than or equal to the length of video. For example, a 30 seconds video needs at least 30 seconds to render. There is also a big disadvantage. Users have to wait until the video rendering process finishes. What it means is that if users would switch to another browser tab, the process will be postponed. If users close the current browser tab, the process will be canceled. Because of those downsides, we had to find another approach, as we don't want to let our users to wait in front of the screens while their video is being rendered. Server-side encoding was our next attempt to create videos. Since we are front-end developers, the easiest way to build a server was starting with Node.js. Besides browser, Node.js is known as another runtime environment of JavaScript and is very familiar to front-end developers. By using Node.js, we can reuse the drawing code base that we have on client side to draw video frames on server side. However, there is a problem. Canvas and WebGL are not available in Node.js. Lucky for us, there are two alternatives, Node Canvas and headless-gl. Node Canvas is a Canvas implementation for Node.js. Headless-gl is WebGL binding for Node.js. This means headless-gl exposes APIs which are the same as WebGL APIs, and behind the scenes, it uses OpenGL APIs to communicate with GPU. With Node Canvas and headless-gl, we managed to solve drawing problem on server side easily, and the same drawing code base can be applied for both client and server. I would like to show you how can we create videos with FFmpeg. After drawing, video frames are stored in GPU memory. To store encoding with FFmpeg, these video frames need to be copied from GPU memory to another place that FFmpeg can access, such as random access memory or solid-state drive. After copying, FFmpeg can read the video frames from random access memory or solid-state drive, and then use either software encoder or hardware encoder to encode these video frames and create video. This approach works, but the process is slow, as we face the bottleneck at the step of transferring data from GPU memory to random access memory or solid-state drive. It takes a lot of time. Due to the bottleneck above, we attempt another method, where we combine hardware encoder with low-level SDK to encode videos. Let's take a look deeper at GPU memory. The area used to store video frames after drawing and the area that the hardware encoder used to read data for encoding are two different regions located in GPU memory. The low-level SDK that I mentioned in the previous section can help the hardware encoder to copy uncompressed video frames from the area that preserved for drawing to the area that preserved for encoding within the GPU memory. With this approach, everything happens on GPU, from drawing to encoding. Therefore, the bottleneck above is completely removed. Let's see, how long does it take to create a 30-second video with three methods above? With media record API, it takes 30 seconds to create a 30 seconds video because it has to record the whole media stream. And by recording, we have to wait for the media stream to play from start to the end. As for FFmpeg, it takes 7 seconds to create a 30-second video, which is already much faster than the media recorder API. As for hardware encoder compared with low-level SDK, only takes 2 seconds. We found that this is the fastest way to create videos among these three methods. In the end, we managed to solve the encoding speed issue by using Node.js as a runtime environment and letting server-side render videos. Not only Node.js is very familiar to front-end developers, but it also allows us to use the same drawing code base for server-side, which is very convenient for maintaining the source code. Using low-level SDK in combination with hardware encoder to copy uncompressed data directly between different regions within GPU memory. Another technical challenge we face is the difference of text drawing results between browser and server. Comparing client and server drawing results, we notice that there is a subtle difference in text drawing, as each platform uses a different text drawing API. We also notice something else. Text drawing results are slightly different between Chrome on macOS and headless-gl on Linux. It was likely because Chrome used different text drawing library for different platforms. We believe that this problem could not be completely resolved right away, so we consider it as a known issue and notify users in advance. And at the same time, we keep researching into this difficult problem. The last technical challenge that we encountered while developing the video editor was supporting new video effects. I will explain why it was a challenge for us. GL shading language, or GSL for short, is the main specific language that we use to control the pixels during the rendering pipeline of WebGL. GL itself code runs directly on GPU, and we use it as a language to develop video effects. As we don't have GSL developers, but still want to satisfy users with many video effects, we use GL Transition open source library. This means unless we spend much time and development cost, we will be limited within the provided effects by this GL transition. In the last section, before ending this talk, I will share a little bit about our next plans. So that was a bit about how we have been working on the editors for Creative Lab project. It's still a long road ahead, and we are still looking at how to make it better by improving what I have just shared above, like apply more GSL effects for video editor to better satisfy our users, support video as a layer for video editor, and of course, trying to resolve the difference of text issue that I mentioned earlier. Scale up the current architecture of the encoding server when the video incoming requests increase. I'm Công Nguyễn, on behalf of Live Creative Lab team. Thank you very much for your listening.